Thanks again, Qiusheng, for joining us today, for sharing about the work that you've done. I will turn it over to you now.
Okay, thanks Diana for the introduction. Hello everyone, thanks for joining. And so for today, I'm going to introduce some of the open source GeoAI educational resources that you can use in your research and teaching. The link to the slides, you can scan the QR code here. I also put a link in the chat, so if you need it, you can come back to check some of the resources. So in the first maybe half an hour, I show you some of the things that you can do with the GeoAI package. And then in the next 20 minutes, I'm going to show you some of the demo that how to get started with the package so that you can, especially if you're new to GeoAI, you want to get started. These resources might be very helpful because they are reproducible and show you step by step from the very beginning how to download the data, prepare your data for training, and also how to train a model and then how to run the inference. So it's kind of end-to-end workflow. And here is the outline. First, I'm going to introduce the package, and then we cover some of the key sections, how to do data acquisition and also prepare data for GeoAI. Then we cover some of the key GeoAI tasks, what kind of GeoAI tasks they can do with the package. And also we briefly introduce some of the geospatial foundation models that you can utilize to do inference without training your own model. Then we go into the live demo and also the Q&A. So the GeoAI in this presentation here specifically refers to the GeoAI Python package. And there are a couple other widely used packages out there that can do geospatial AI. And my goal here is to simplify the process. So if you're someone new to GeoAI, you want to get started, you probably want to try this one out because it has been much easier to get started compared to other packages. And I only started this one maybe about 2 years ago. And the goal is to make it really easy for everyone to utilize geospatial AI with geospatial data. And although there are some other packages, but they're not very easy to use and they require a lot of coding. So the GeoAI package is trying to simplify the whole workflow so you can see the data interactively. You can also run some of the workflow just with couple lines code. So most of the workflow that I'm going to introduce here in today's section is usually just maybe 5 to 6 lines of code that you can start running your AI models. And for complicated workflow, they might need to write more, but in general, you can just utilizing this to get started. And also there is a QGIS plugin, although it's not the focus of today's section, but if you're someone that don't know coding, you can also use the QGIS plugin to just run geospatial AI without writing code directly using the interface. And it's a Python package, so you can install it using pip or using conda. It has been pre-installed in the I-GUIDE platform, GeoAI, the EDU kernel. I'm going to show you how to utilize that later. But if you have your GPU on a local computer, or you can also use on other platform as well, as long as they have Jupyter installed and also, for example, Google Colab and other platform as well. And it does require the GPU to be able to run much faster, otherwise it will be much slower. And so first, let me talk about some of the data acquisition, the data downloading. So in order to train your AI model, you need to have geospatial data. And in this case, for example, if you want to train a building detection model, then you probably need some high resolution satellite data and also some building footprints, something like this. And you can get data from a variety of sources. One of the popular one is the Microsoft Planetary Computer, because they have a lot of satellite data and also air imagery. Especially in the US, we have this high resolution, 1 meter resolution data from the USDA for multiple years. So you can download data for free. In terms of building data, transportation, and point of interest, I would suggest the Overtour Maps data, because this is a new initiative by a lot of tech companies, and they produce a large amount of open access data built on top OpenStreetMaps. It has been updated, and if you, especially if you need building data, this is probably the best resource that you can get right now. And you can use the GeoAI package here. All the slides I'm going to show you has a notebook on the slide, so you can click the link, take you to the notebook. And also later I'll show you how to use those on I-GUIDE platform. But in general, this is what you need on the lower left corner here. Shows you some kind of a snapshot, like how do you actually download data. So all you need to do is just to specify a bounding box, for example, well, what your area of interest, then just call one line of code to download the imagery from a plane to computer, and then also download the building data. So essentially, you just need 4 lines of code, then you can get the data downloaded. And of course, for the net imagery, this one is just for the United States, but you can also download Sentinel. You can download other data for other countries as well, as long as the plane to computer has data available. So once you download the data, then you can visualize the data easily. Just with 1 line of code, create split map, for example. I can visualize the building footprint with the aerial imagery, just with 1 line of code. If you're using other packages, this might take you 10, 20 lines of code actually just to create visualization like this. So we simplify the process that allows you to easily see the data interactively rather than just print out a static thumbnail, because sometimes for segmentation stuff, you might want to actually to see the data interactively, zoom in, zoom out, so that you can see more details of data. And again, every slide has a notebook, so feel free to try them out. And once you verify the data, they are in good quality, then you can start creating training data. Because different from traditional machine learning using GS software, you cannot just feed the entire imagery or the entire vector data into the deep learning model, because for deep learning model, you require on GPU. So GPU is very limited. And so the common like practice is to subdivide your images into smaller so-called image chips. And then you're going to basically feed the image chips into the model. And so once you finish all the image chips, it's called one epoch, but you will need to do multiple epochs. So because the data, you sometimes you need to randomize the input data, otherwise it's going to be overfitting. So once you pass multiple rounds and then start training the model, then the model is going to get better and better. At a certain point, then you can stop training. But in order to create the training data, you can call the GeoAI function. So again, just 1 line of code, you can export the GeoTIFF task. All you need to just provide the input, for example, the raster imagery, and also the input, in this case, is the building polygon. So for example, we have two data set, the raster and then the vector, okay? On the upper left corner here, the vector is also overlaid on the raster. So you have the imagery, you have the building, and then just call this 1 line of code, you can create the image chips. On the right here shows you some kind of overview. So what we are trying to do here is to create image chips, but you also need to make sure that the image chips have some overlap between the adjacent tiles, because otherwise you're going to have some artifacts along the border of those images. So usually you want to maybe have 25% overlap between the image chips. So just with this 1 line of code, you can create image chips here, like what's being shown here in the lower right corner. That means it's basically doing the sliding window from the left to the right, and it's going to also convert the vector data to raster. So in this case, we have the building, one image chips. You also have the corresponding building mask. So in this case, just binary, black and white. So it's just very, very simple. So it can help you prepare the training data easily. Otherwise, you might need to write hundreds of lines of code just to prepare the training data. Is quite frustrating. So the package simplifies the process so that you can focus more on training the model and also run the inference, rather than have to do a lot of data processing, how to do the reprojection. So the function handles all the reprojection. So if the data in different projection, you can do it for you. And for vector data, it's going to convert to raster and also align them all together so that you can just create nice looking training data, just 1 line of code. Once you have the training data, then you can start talking about the GeoAI. So what kind of things you can do? These are 7 like core GeoAI tasks that you can do with GeoAI. There will many more, but these are some of the very common ones that are being utilized. And I'm going to show you some of the use cases. So next time when you have some problem that you want to use GeoAI, you know like what kind of task it is. So you need to basically understand the scenario for the use cases for each task. And the first one is image recognition. So this one in the computer vision literature, this is actually called image classification. And it's kind of confused with the remote sensing image classification. They are kind of very different. So I kind of just use the image recognition term so that it's not confused with image classification. And the idea is very simple. Give you one imagery, you want to give a label, a text label. So it's not really like classified by pixel. It's classified every imagery by a single label. And this is especially popular in the early stage of deep learning because at the time we don't really have semantic segmentation at the time yet. So giving one imagery, you give a label. For example, on the right here shows you 10 image chips, right? And so for each one, it can be, for example, crop, it can be forest, it can be urban, it can be industrial, residential. So giving one image, you just give one label. So this is the classic image recognition task. And nowadays, it can still be useful because sometimes if you are trying to quickly scan your imagery and you're trying to find out some objects within the imagery, you don't necessarily have to classify every single imagery. For example, let's say I want to detect the buildings, and you probably don't want to classify every imagery because not everyone has buildings. So you can use the image recognition because this one is very fast. So and you can quickly scan the imagery and only find out imagery that has buildings, and then you can do a second step to do the segmentation so that you can get building footprints. But in here, using the package, just one line of code, just call this train image classifier and then just passing your image directory, the data directory. So the data directory is the one that we, for example, you can create from the previous task using the prepared training data, or you can point to your own data, and all you need to just figure out, okay, what kind of model we're going to use, how many epochs, and how the base size. So these are some of the common basically deep learning parameters that you can customize. You can also customize how many channels. So channel basically RGB, or you can have multispectral or hyperspectral. So all you need to just to customize all these parameters, and that's it. So basically giving one function, you can customize it to whichever way you want, and then you will start training the model. Once you finish the training, then you can do the validate the evaluation of the model. So on the right here, show you some of these kind of training and validation laws, and also the accuracy. In this example, I only train for 5 epochs, but if you have time, you have a GPU, you can train a lot more. So ideally, what you want to see is that your training accuracy is increasing, and also the loss is decreasing, or the validation accuracy also is increasing. So this is a good sign. So our lower right corner here, you can see that the blue line is increasing. That means your training is getting better and better. And this is what you want to see. If you see the line is like fluctuating or is decreasing, then probably you need to adjust some of the parameters, or maybe your data quality is not very good. And but in general, you're going to easily produce some of these kind of graphs so that you can see if your model is actually doing a good job or not. And after that, you can do the create, or you can evaluate the model. You can create so-called the confusion matrix, right? So in this case, it's just like one image is one label. So we have, for example, we have 10 classes, and overall, this is kind of similar to remote sensing classification, like pixel-wise classification. So you can also see in the diagonal line here, you want to see the darker color because you ideally you want to see all of them being classified correctly. So for example, some of these in here, industrial and also residential. So you can see this one. For example, it's the label, for example, it's like all residential, but you can see a lot of them as actually being misclassified as industrial. Sometimes the building, but the image resolution might not be high enough, or maybe the label is not good enough, or maybe quite confusing. So you might see some of these. Then this is where you can go to improve your training data. But overall, you can see here, it looks pretty good. Most of them are being classified correctly. That means the model is doing decently. and you can then use that to use that to run inference on other data sets. So this is just a simple like image recognition task. So prepare your data and then just code one line of code to train the model, and then you can run the inference. But image recognition is nowadays not that useful, especially if you have high resolution data. You want to get more. You can only get more fine resolution result rather than give your label, because giving a set of imagery, you might only detect, for example, how many objects within the imagery. Rather than say, okay, this imagery has buildings, you want to see how many buildings are actually there. So this is the second task called object detection. Object detection basically output the bounding boxes and also the probability or the confidence score for each building. So upper right corner here, you can see some of the examples in here. So, for example, you want to detect airplanes, right? At the airport, then you can provide one imagery, and then you will be able to detect all the bounding boxes, something like this. It can be any object. It doesn't have to be just airplane or ships or whatever you like, as long as you have the training data. Again, one line code here, just train the multi-class detector. That means your data have multiple classes, or it can be just one class, black and white, or yes or no. Or sometimes if you have multiple, then you can use the multi-class detector. On the right here, similar, you can see the training loss is decreasing, validation, it might be fluctuating because sometimes if the model is overfitting, then the validation might be fluctuating. But also you can see the result here looks pretty decent. And so but object detection is kind of at the intermediate step, right? So again, here, it'll be much nicer if you can delineate the exact boundary of the airplane rather than just giving a bounding box. So the next one, this one is probably the most commonly used deep learning task in remote sensing. It's called the semantic segmentation. So this is the in the computer vision, it's called semantic segmentation, but in remote sensing, it's actually image classification, pixel-based image classification, or you can say also object-based, because deep learning, you can actually do object-based segmentation, but it's kind of a combination of pixel-based and also object-based segmentation, but it's called semantic segmentation. So in here, it's basically for giving one imagery, it's going to classify every pixel, not just the bounding box. And what you need to do is just call this one, train segmentation model. And then for the input data, you can provide your input images. So those are the data that we created in the previous slide, that you call the function to create the training data. You also provide the label and then just provide the output. After that, you can specify the model architecture, the encoder, and also the weight. So essentially, there are a lot of models out there already being trained on other data. They're not necessarily trained on geospatial data. But the nice thing about deep learning is those weights sometimes can be transferable. So because essentially doing all the segmentation here task is doing some kind of pattern recognition, and a lot of like pattern recognition, they share similarities. So basically you're detecting the boundary, the shape, and other stuff. So all you need to do is just use those so-called pre-trained weights so that you don't have to start from scratch. And then we're basically utilizing our data to do the fine tuning. So that's why it's very important that you always use some of the pre-trained weights that are more suitable for your task. In this case, we're using some of the popular one, for example, the image that have been trained on a lot of high resolution photos. And then we just utilize this one just with couple epochs. So on the right here, you can see this is how the training goes. So you can see the loss at the beginning, it kind of fluctuating. And then the IOU means is the intersection over union. Basically means your prediction overlap, the overlap between your prediction and also the reference or the ground truth. So you can see here 0.7 basically means like 70%. That means your prediction has almost 70% overlap with your ground truth or your reference. You want to target at least maybe 60, 70, ideally 80, 90%. So that means it has very good overlap. But sometimes it depends on your input data. If your input data quality is not very good, you're not going to get a very high IOU. But overall, this is what you're going to see on the four plots in here. You want to see them increase. That means your model is getting better and better. So at the beginning, it's fluctuating because it's trying to fine tune the model. And if you're new to like deep learning, I can give you an analogy. So you can think about you are someone maybe at the top of the mountain, you're trying to get to the bottom, and along the way there might be many paths. So what you want to find is to find a shortcut that can get there faster, but also in the meantime that is safer. So you want to go like too steep, that means sometimes you're going to fall down. That means this is how it's why it's fluctuating. So it's in along the way, it's going to figure out a way optimize. So basically, it's an optimization process. So you want to make sure it's safe, but you're also going to be accurate. And overall, this is what you're going to get. So an example here shows you, for example, we're going to do building detection. So we train the model using the unit model, and you have some of the building bars that you get or you downloaded it, and then just train the model. Then after that, you can just run this semantic segmentation to just run the inference. So essentially, just with two lines of code, train the model and then run the inference. That's all. You don't have to worry about how to actually put all the architecture because for most users, you don't really care too much about how the more architecture works. So, for example, you're using ChatGPT or Gemini, all you need to do is just focus on just give me an answer. I don't really care about how ChatGPT actually functions. You don't really need to know all the underlying architecture or how the GPU works. You give your question, you get an answer. And so this is how it works in the package. There's two lines code, you can get that. And then after that, you can do some post-processing. For example, here I want to rectangularize the building footprints. Then you just code one more line code, regularize, and then you'll be able to generate nice looking building footprints for you. And so you can compare the result, for example, before and after. Because deep learning, although it's kind of like object-based, but it's still many of the object generated, you are still going to have very pixelated boundaries. And so if you want to produce nice looking results, then you need to do some post processing. Also, you can calculate geometry properties. For example, you want to figure out how many buildings, what's the size of the building, what's the median size, what's the density, something like that. Then you can certainly also just call this one line of code, add geometry properties. Then you can calculate all those things for you so that you don't have to manually do the calculation. And after that, you can do the filtering because if the result have some false classification, you can use the attribute to filter out. For example, there's many like tiny objects, then you can just do a threshold, then you can remove them using some post processing. Um, so semantic segmentation has a variety of use cases, and so you can apply it on remote sensing data or in JPEG, PNG images. So in early days, many of the benchmark data set actually just PNG, JPEG that without geospatial reference information. So you can do the same thing. So it's the same workflow you hear, the same function. Then you can just, for example, I want to train a water segmentation model. If you have the data, then you just train the model and then just do the segmentation. Or you can also apply on remote sensing data. So in this case, it's Sentinel-2 data multispectral, 6 spectral bands. So the same function, the same workflow. All you need to do is just to change this one number of channels, change to 6 because it's not RGB anymore. It's not 3. So, and for number of classes, in this case, it's just water and non-water. So it'll be just 2. And other than that, you can just use the default settings and then just let it run. You'll be able to get the result. And so here shows you, for example, the prediction is the one in the middle, and then the ground truth is the one on the right. Again, there's an over here if you want to reproduce. And this one is pretty good. So you can see we only train maybe 20 epochs. After 3 or 4 epochs, you can see the big spike in the IOU. So that means at a certain point, the model just figure out, okay, this is the way to go. Now I can just go along this way. Then they just continue to train the model. And if the model is not improving, you can also set like early learning, like stopping criteria. So maybe after a couple epochs, then we just stop, say, okay, this is enough. And it's this simple, just 2 lines of code, you can train your model. Besides satellite data, you can also apply on air imagery. For example, this is 1 meter resolution air imagery. So I can train the model to detect water and wetlands. Again, you can see here the same function, 2 lines of code. In here, I just changed the number of channels to 4 because this is just RGB and also near infrared band. So very easy that you can customize to apply to any data set using the same workflow. Another very common application is lane cover classification. So it's the same here. I use the 1 meter resolution aerial imaging, but in this case, it's 13 classes because it's lane cover classification. So again, you can use your own lane cover classification data or label as well. And so just with same lines of code, then you can train the model, you can apply it to delineate updated lane cover classification as well. And all the example that I showed previously require you to have training data and also training label or mask. But there are also some recent models that kind of like pre-trained models that has been trained on different sensors, different data. So you don't need to train the data. You don't need to train the model. And this is called sensor agnostic segmentation model. So in this case, it's the water segmentation model based on Omni water mass. And so you don't need to train model using your water mask. You can just provide your imagery and then just call this one line of code. So in this case, just two lines of code. Import the GeoAI package and then just call this function. Segment water and then point to your imagery. It can be Sentinel, it can be StainSet, it can be air imagery, it can be drone imagery. Uh, and then it's going to generate the result. And then you can just visualize the data here, one line of code. So essentially, it's a three lines of code. You can do water segmentation on any imagery without having to train your own model. You can also do another one. This one is based on Omni Cloud Mask. And so in remote sensing, if you need to train the model, sometimes cloud optical data has a lot of cloud coverage. And if you're trying to delineate, do some semantic segmentation, make sure you exclude cloud because otherwise you're going to contaminate your training data. You're going to make a result much, much worse. And so in this case, this model can actually predict the cloud mask and remove the cloud from your data so they can mask them as known data rather than enter them into the training model. Again, just one line of code, predict the cloud mask from the raster, and then just pointing to the data, generate the result, then you can get the result easy. So these are the two pre-trained models that can be useful. That if you don't have your data, all data to train the model. So that's called the semantic segmentation, pixel based. But the problem is that sometimes it's not enough because in this case, for example, here I want to do the crop, the so-called agricultural field boundary segmentation. So in this case, all the boundaries are actually adjacent to each other. If you're using the semantic segmentation, they are kind of segmented one single object and it's not enough because you want to see the individual one. So if they're adjacent to each other, if there's a boundary, you want to segment as separate objects. So in this case, this is called instance segmentation. So it's one step further, even though they all belong to agricultural field, but they belong to different unique different polygon boundaries. So in this case, you want to use the train the instance segmentation model and the same function, the same workflow, a different function, but it's the same workflow. So train the instance segmentation model, then you can run the inference. One thing to keep in mind is this one is very computationally intensive. So you need a lot more GPU to do that because you are doing multiple rounds of object segmentation rather than just like semantic segmentation, just one round. And another one is called image translation. Image translation basically is the task of converting one image from one domain to the other. So super resolution is one good example. Basically means you are converting image from a coarse resolution to a high resolution imagery. Or there are also other cases. For example, you're converting a side imagery to RGB or multispectral, or you're converting from multispectral to hyperspectral, or something like that, or you're converting from black and white to RGB, something like that. So in the computer vision literature, this is something that's basically very popular. And so, for example, you can turn your very old photos into kind of looks like a new one. But this is not really remote sensing, original remote sensing images. This is basically produce some good looking, but don't try to use this one for quantitative analysis because it's not real remote sensing data. It's just based on the probability to show you. For example, we can down sample the Sentinel to 10-meter resolution to 2.5 meter, so you can see it's much sharper. And this sometimes can be useful if you want to get some higher resolution imagery out of coarse resolution. But just to keep in mind, it's just nice looking, but it's not good for remote sensing analysis. Another use case is change detection. This is also very common. Given to set imagery, you want to see what has changed. So in the GeoAI package, we also have function that can easily allows you to do change detection based on some other model, for example, change star model. So this is an area in Las Vegas. You can see the imagery in 2019, 2012, and just with couple lines code, you can detect the buildings, and then you can also see the changes, for example, new buildings. And this can be very helpful for disaster management, urban planning, that you want to quickly see the change area. Then you can just utilize this to quickly get result. And also show you here, depends on the threshold, you might get different result, but in general, you can see, for example, the pink color here in the lower right corner, this just shows you basically the new residential buildings in the region. So in that way, you don't have to train your own model by yourself. You can just use this one to get some quick results. And besides that, you can also do pixel level regression, because all the previous examples I show you is mostly based on segmentation, and basically the categorical segmentation. But sometimes you also want to do some tasks to predict crop yield, vegetation, temperature, something like that. So those are more like continuous prediction. It's not like binary or integer prediction. And again, the package has a function that allows you to train a pixel regressor. That actually means giving an imagery and then go to predict numerical values out of that. And so in this case, I can giving, for example, I know I'm using the NDVI image. I can train the model actually to predict the NDVI, but it's not using the NDVI equation. But you can do this other similar use cases. For example, you can predict the temperature. You can predict the water depth or the bathymetry depth or something like that based on some in situ data, right? So because you might not have water depth or bathymetry for all the pixels, but you can train the model to predict that if you have some training data. And this is another example using the crop canopy height estimation. So giving an area imagery, you can predict the tree height, even though you don't really have the LiDAR data to actually have the accurate height, tree height. So you can do this one. Again, this is just the prediction. So it's you depends on your location. You might need to verify it, but if you don't have any data, you really want it, this is certainly something you can utilize. So the canopy height model is already pre-trained, so you can apply to any imagery that you want. So that's some of the seven core GeoAI tasks you can do with the model. And in the last year or two, we also have a lot of development in the so-called geospatial foundation model. So I'm going to quickly show you some of those, so if you are interested in. And the first one is very popular, it's the segmentation model. So this one is actually not geospatial foundation model, but the model is so powerful that you can easily do transfer learning to do segmentation on remote sensing data. So I developed the SamGeo package, but it has been also integrated into the GeoAI package as well. So you can just use that to do segmentation without training your model. So foundation model means that it has been trained on tons of data, and you can just use that to do some downstream tasks easily without having to having your own training data. So in this case here, I give you this imagery. I want to detect buildings. Then, I mean, in the traditional deep learning task, you need to have the building mask. But right now, I don't have to. All you need to do is just initialize the model, set the imagery, and then just say, use a prompt building. That's it, 4 lines code, and you get the result. So you don't have to train the model, and it give you basically the probability here, the confidence score. And so each building has been detected, and if this like have a lot of false classification, you can filter by the probability, remove those like false classification. So again, like going from training your model take a lot of time to just coding the model itself. And again, it's not geospatial foundation models exactly, but you can just use the prompt building to be able to detect all the buildings for you. And then this is kind of the probability mask. So the red color represent higher confidence, and then the light blue color represent low confidence. And you can certainly see this not perfect, but if you want some quick result, this is something that you can easily get easy using the model. You can also do bounding box. This is also very powerful, because sometimes you don't really have a good prompt to utilize, and we want to find some object. So in this case, all you need to just say I draw a bounding box, okay, with around this object, find all the similar objects within this imagery. And what you need to provide here is just a bounding box. And then you'll be able to detect all the buildings for you. So very, very easy. So you can use to detect trees, buildings, and water, or anything you like. All you need is just give you a reference. Okay, this is the reference object. Get all of them. Very, very easy. You can also use a vector data, a bounding box. So you might have the bounding box from other data sources or from other deep learning model, but you don't have the perfect boundary, right? So it's just a bounding box. So in this case, I have the bounding box of all the buildings. Then you can just, again, one line code, provide the bounding box, and then you will get the segmentation task for all the buildings for your imagery. Or you can just use a centroid. So in this case, I don't have the training data. I only have the centroid of each building. Then you just pass the one centroid, and then we get all the buildings for you as well. This can be very, very helpful if you're doing like digitization. Rather than having to draw the building manually, now you can just dot, 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 dot. So you can basically create training data very, very fast, and then use SamGeo to quickly generate the segmentation mask rather than having to spend a lot of time trying to create a training model. You can also do base segmentation. For example, I have like 100 images. I want to detect all the buildings from all the images. And then you can just one line code, generate mask base, and then just provide the building prompt, and that's it. So just three lines of code. You can segment 100 images, 1,000, 10,000, or million, doesn't matter. It's just the same workflow. So you can see how this can really make things scalable and fast if you have the model that can be suitable for your task. You can also do interactive segmentation. So the package also has functionality that allows you to quickly, for example, I can draw a bounding box and then just click one button. You will segment all the object within the image for you. And this is very powerful because you can quickly do some prototyping. You can detect buildings, you can detect trees, and then you can figure out what's the optimal parameter that's best for your use case. And for example, I can just select one object and then detect all the trees. If it's not enough, you can adjust the parameter, and then you can basically iterate until you find the good parameters for your imagery. And then besides just like one object, sometimes, for example, you want to find some rooftops, but the prompt doesn't give you good result. Then you just throw the boundary box, and then you'll be able to detect all the object for you. And this is all on the fly. This is not like speeding up. It's running on the fly. So it's very, very fast because the model has been trained. So all you need just to encode the imagery. And then after that, you can run tasks very, very quickly. And you can also export the data as vector data. So it can be GeoTIFF or can be vector format as well. So then you can just integrate into your GS workflows. Besides SAM3, there's some other vision language model available. So this one is called the Moondream VUM. It's also very interesting because you can use that to do ask questions. For example, you can ask how many buildings in the imagery. So you'll be able to figure out and do the detection. So this is similar to ChatGPT and other model that can do vision reasoning. So that means you will be able to understand the imagery and then do it for you. But the difference is this is open source. You can actually download the weight and you can run it locally without to have a subscription. So you can, for example, detect all the trees, detect all the buildings, detect the roads. You'll be able to do that for you. But keep in mind, this is not going to be perfect because the model is not really trained on geospatial data. So it's suitable for high resolution imagery, but it's not very good for coarse resolution, for example, Landsat and Sentinel, because the model, the image looks very different. But for high resolution, it's pretty decent. And we also have recently a sort of satellite embeddings. So embedding basically you can think about is just a compact representation of the data. So the model basically has been trained on a lot of data, and then could generate a lot of like so-called satellite embeddings. That means just numerical vectors representing the data, and so you can use that to do a lot of downstream tasks. For example, find similar objects or find change detection. Maybe I can give you a analysis like you are attending my presentation here today, and I introduce a lot of concepts. But probably you're not going to remember everything. But your take-home message will be like, okay, you can do a lot of like GeoAI tasks, and it's like very simple, couple lines of code. And later, okay, I need to do segmentation. Then you can come back to see, okay, I find this slide, then you can use the example in here. So it's very similar concept. It's basically training a lot of data. It's an abstraction of your data, and you lose the details, but you have some high level abstraction so that you can quickly use to, for example, I know this object, find me all the similar objects. You will do that for you, but it doesn't know what it is. So set embedding doesn't really have classification or supervised mass in there. It just know something is similar to something else. Depends on the numerical vector, basically how far they're away from each other. So the human need to assign the label. For example, you can say find this object similar to the other one, and you find all the object for you. Then you can say, okay, this is buildings. Then you assume all those are basically buildings. And one of the very popular one is the Alpha OS Theta embedding they were released, I think, 2 years ago. And so it's been integrated into the package, so you can actually visualize them interactively using the package. So the embedding has 64 channels, so it's 10-meter resolution at the global scale, so you can visualize the data easily within the notebook environment, and you can see how it looks like. But again, you see all the colorful things in here. That just means each color. If they're similar color, that means they're similar to each other. But the model itself doesn't know this is mountains or building or trees or water. It just know that they are similar in that particular channel. So you can basically adjust the different band combination, or you can do a principal component analysis to do the reduction so that you can use it maybe to do lane cover classification or to change detection or something like that. I don't have time to get into details, but this is like still a lot of new models coming out, new set embeddings, but they're very much all the same. That's similar. It's basically a bunch of channels and then pixel values, and then you can use that to do downstream applications. So in this case, for example, I can do the change detection between two time periods, 2017 and 2014. So you don't have to train your own model. You just use the foundation model and then just do the multiply, then you're going to figure out, for example, whether they are similar to each other or not. Darker color means they are not similar. Bright color means they're similar. So in this case, you are trying to figure out, for example, crop changes in the same area. This one can give you some insight. That means during those 2 years, something has changed in that location. If it's very dark color, that means it has changed. So this can give you some of the signal that you might want to see. For example, if there's any new construction, new buildings, or new crop or something like that, you can quickly find out without having to train your own model. And you can also do clustering. So this is called the embedding clustering, similar to the imagery that I showed you earlier, right? Similar color, so you can use that to do the reduction. So you can easily find out, for example, if they are very close to each other, you're going to have clustered together. That means it might be maybe trees or building or something like that. So then you can use this one to assign the label. So this is unsupervised classification. So basically just clustering similar pixels into one class and then you assign the label. So this is how people use the set embeddings to do downstream lane cover classification. So for example, this shows you all the embedding, for example, the clustering around San Francisco. So you can certainly see the model doesn't know its buildings, but you can see some patterns in here, right? Different color. For example, the pink color might be just urban buildings, or maybe other might be trees or other stuff, and just give you something that you can easy. If you don't have data for your area, this might be something you can easily get. Like I want the lane color classification for this year, for that year. Then you can use this one to quickly generate some results. Okay, so that's all I want to show you here. And next, I'm going to show you how to get started. So I create some of the notebooks and put it on GitHub and also on I-GUIDE. So let me show you here. If you go to the iGuide.io platform here, and then if you click the open the platform, and from here, you can find all kind of the notebooks that people share on this platform, and you can start exploring some of these notebooks, or you can just do the search, for example, GeoAI, and then you can start finding some of the example. And I put some of these in here, so you can click any of those examples, and then it will take you to the website, or you can also just click, I think on the slides, you can just click the link to the GitHub here and also to directly to the I-GUIDE platform. So if you go to the GitHub, all the notebook examples are available from here. So I have 13 examples. covering all the use cases that show you from the beginning, how to download the data, how to visualize the data, create the training, and then some of the core GeoAI tasks. And one thing I want to point out is to make sure that you use the GeoAI EDO kernel. So this is the one created by I-GUIDE specifically for running some of these examples. And for other kernels, they might not have the dependency installed properly. So you want to utilize this one. I'm going to show you how to get started. So for example, here, you can maybe let me go here. And then, so for example, if you go to the I-GUIDE platform and you find any example you're interested in, then you can click any examples here on the page, just click run the notebook. It's going to take you to the JupyterHub, the I-GUIDE JupyterHub. You might need to log in using your EDU account, or I think you can also use your ORCID ID or something like that. Once you log in, then you will open the notebook, you will clone the notebook, and then open the notebook directly within here. And the first step you need to do is to make sure you go to the upper right corner here, and then select this one, GeoAI EDU kernel. So this is the one that you need to select. Don't use any other one. So select this one and then just yes. Also, I recommend that you want to just uncomment this one, Control Slash, and then to install the dependencies to install the updated versions. Although the kernel has already installed some of those dependencies, but sometimes new dependencies might break some of the workflow. So you want to basically update them, and after that you can just restart the kernel, clear all the outputs. Um, and so here, I have some of these code blocks. These are not really necessary. If you're running on other platform, it's specific just for the I-GUIDE here because some of the dependencies conflict. So you will run into some errors later on. But if you just run this one at the beginning, and then you don't have to understand that it basically is just dealing with some dependency conflict issues. And so just to make sure things are set up properly. And after that, you can just run through the notebook, for example, import the GeoAI package, and then you can download the data. So this notebook specifically is just for creating the training data. So it might take a couple seconds to download the data. You are welcome to utilize your own data as well. So once the data is being downloaded, then you can use to, for example, I can visualize the data using just one line of code. So you can visualize data using as a static imagery, or you can also visualize data interactively. I'm not okay. So now you can see, for example, this is the 1 meter resolution air imagery that we downloaded it, and also we can also visualize the vector data as well. So this is just the building polygon overlay on top of the data. Imagine this is the input data that you have, and then you want to train a model based on this sample data. You can also view the data interactively, so you can also overlay the polygon on the base map. So this one shows you all the building outlines. Basically, it's based on OpenStreetMap, so you can see all the building polygons here. And after that, if you want, you can also convert the vector to raster if you want to, but you don't have to. So GeoAI handle that for you, but I'm showing the steps here is like what it's doing under the hood. And after that, you just call this one line of code. So this is where you prepare your training data for deep learning. So just call this export geotiff types. It's going to basically just take these two imagery, this one and also the building, and you're going to do the slicing and then create the training data. So you don't have to worry about how to do that by yourself. After that, you're going to find the output directory here. For example, this is the output directory, and all the data have been output to this directory. So you're going to see the images, you're going to see the labels. So basically the building mass, it has been subdivided into one by one. And you can also see for example, the tile overview. So this is how it's doing basically the tiling, the slicing. You can see some overlap here, 25% overlap, and you can see the building, also the bars. And this is essentially what's needed in order to train the model. And if you want, you can also get a quick look about what it looks like. So for example, this is the building, this is the mass, this is the building, this is the mass. And after that, you can just pass this one into deep learning models. But there are also a lot of other cases that it's not necessarily one imagery and then one vector. You might have multiple images, one vector, or it might have multiple images, multiple vector. The package has example for dealing with multiple cases. For example, I have multiple images, and I also have one single vector covering all the images or multiple vector. So just for examples, it covers most of the use cases. It doesn't matter what data input you have, and then you just utilize this one to generate um, uh, the training data, and then after that you can just go to open other notebooks. Then you can start training a model. For example, you want to do object detection or you want to image segmentation, then you just follow through. For example, here, this one is just for the image recognition, right? So you download all the data, and some of those are basically kind of a blank, but you can start training the model. It might take a while if you don't have the GPU, but you can certainly utilize this workflow to do training. I can also show you here. For example, I run it on my local computer, and you can do that for any task, image recognition, or you can do maybe SAM3 segmentation or other semantic segmentation. So there are a lot of example you can run through. For example, can show you this semantic segmentation. So you can download the data, and you can just run through all the models step by step, training the model. So here, for example, just um, let me show you, like just pointing to your data, the example, download the data, and then create the training data, train the model, evaluate the model, and then just run the inference. So this just basically 5 or 6 code blocks, and then you can get the work done. Then you can visualize the result. You can also do some post-processing if needed. So you can just run through the notebook on your local computer, on I-GUIDE, on Google Colab. As long as you have the GeoAI package installed, then you should be good to go. And the notebook also has a lot of use cases: service water, building, lane cover classification. There different use cases that you can adapt to your own examples. Again, so you can find all the 7 key GeoAI tasks, and also 3 geospatial foundation models, and also satellite embeddings. If you run into any issues, feel free to post issues on either here or on the GeoAI package. So I can quickly show you if you go to opengeoai.org. So this one also has a lot of examples in here. I think maybe 70, 80 examples, but I have compiled all of them and then put it on iGuide. So basically, each notebook give you end-to-end examples on how to do GeoAI tasks. If you run into issues, then you can open issue here on GitHub, and I'll be happy to look into that. And yeah, that's all I want to show you. Again, I don't have time to get into each individual one. You're going to take some time to run all the notebook, but feel free to utilize them, customize them to your own data, and let me know if you have any questions. Okay, thank you very much.
Thank you, Qiusheng. Is there any questions from the audience at this point? And while you think of your questions and you type them into the chat, or you could raise your hand and unmute yourself. Just as a reminder, so Qiusheng is one of the community champions. Currently, his notebooks within the I-GUIDE platform are tagged within the collection of notebooks, but they're going to be shifted over to what are called open educational resources. So under knowledge elements are all the different types of digital content that the platform holds, and his notebooks and the others that are part of the Community Champions program are going to be under educational resources that are here. Because we know they're used for a lot of research activities, but they're part of our educational team here at I-GUIDE that's been sponsoring our Community Championship program. So terrific collection of materials here, models, embeddings, foundation models, tasks, things that can be combined to achieve different tasks. And we really appreciate this being, we're able to access this via the I-GUIDE platform as well.
So also all the notebooks, so basically I-GUIDE pull from GitHub directly. So all the notebook, if I update it on GitHub, you also will automatically update on I-GUIDE when you click the link. So you can also follow the GitHub, clone this one to your computer as well, or to I-GUIDE as well.
Yeah, thank you, Qiusheng, for that reminder. Can you put that GitHub link there again? Perfect. Okay, if there aren't...
The links are also on the slides. So if you go to the slides,
Yes.
I also put it on here, so you can also find them from the slides.
Right.
And I think the most maybe the barrier for beginner is to set up the environment, install the dependencies. That one is always tricky because GeoAI depends on a lot of other PyTorch dependencies, especially if you want to utilize GPU. And it basically, when you install the GeoAI package, it install hundreds of dependencies. And sometimes if some packages they update it, sometimes you might break other packages, make like incompatible. But in general, you can just use Conda to install, and then everything will be pretty smooth. But once you pass the installation issue, then you can start adapt the notebook, and then you can apply your own data, run the model. So the goal is to make it really easy. So not everyone know all the technical detail how to construct a model yourself. But if you want just some quick result from your data, this might be something that can save you a lot of time without having to go through all the steps trying to construct your own model architecture.
Right. Okay, quick question from Sina. Sina, I see your hand raised.
Yes, thank you, Diana. Very, very, I mean, this is just a random question. I'm not too sure if such a thing exists or not. Have you came across any AI like segmentation that's texture based, not semantics or basically pixel value based, like based on the neighborhoods?
Pixel value is based on neighborhood.
Yes, texture based, like I don't know, like fractals or those type of classifications.
Yeah, you can use some of the pixel level. I mean, you can train a model using the pixel regressor. That one might be useful. So it's certainly something, but it's not necessarily rely on all the pixels, because if you're doing the semantic segmentation, it's going to basically figure out the neighborhood, which one can be grouped as one single object. But if you're doing the pixel level classification, like a regressor, it's basically just going to based on the pixel. So we don't have a whole lot of those, but you can certainly also try the theta embedding. Theta embedding is actually they combine both. They can find a similar objects. So if your interest is to find some object, you can just find the same object, the reference first, and then you ask the set image to find all the similar ones. I'm not sure if you answer your question, but I don't have a concrete example to show you right now, but
Yeah,
I would suggest
yeah,
you try the set embeddings, because the embedding has been trained on a lot of data, so it might have some signals in there. If something is similar, for example, based on the surrounding, if you find object, and then you will find all the similar objects in the same region.
right. Yeah, it's a very niche use case, and yeah, yeah.
If not, you can train your own model. You can have your train your own. You just need to have training data. That's it. If you have training data, then usually the model will be able to train and then detect that based on the neighborhood.
Okay, thank you.
Can I go ahead and ask a question? I don't see the emoji for raising my hand.
Okay, yeah, no, please go ahead.
Yeah, nice seeing you, Sean. This is Tedros. So I have a very general question. So I know GeoAI is a Python package. So does it utilize, I think my understanding is probably to utilize some sort of fundamental AI models, large language models? And if so, which ones does it use? And also, how do you, like, this is more of like a general question again. How do you see like the integration between AI and geospatial analysis in terms of like agentic AI in geospatial domain moving forward?
So the package right now, this is what I present here today. Mostly is just like those traditional GeoAI tasks, but there's also some development in GeoAgents. It's not the focus of the talk, but if you're interested, you can go to GeoAI, geoagent.org. So this one is focused on but it's not really doing like, it's still kind of GeoAI, but it's not really doing like segmentation or object detection, but it's doing like using natural language to find the data, visualize the data. So if you're interested in, you can check out this new package called GeoAgent. So this is another one that I just started maybe 2 months ago. So it's still under active development, but it has a lot of powerful features that you can just describe your natural language to find satellite data, aerial imagery, and then you can visualize them. You can run some analysis, and you can also run GeoAI as well. So you were able to pull the data and then you say, okay, detect all the buildings. You were able to detect using the GeoAI as the backend to do the segmentation. So, but it's still under development, so it's not. You also have the QGIS plugin. If you're interested, you can use the QGIS plugin here to install it on a computer. Then you can just say, okay, find imagery covering this location for this time period, something like that, and then you'll be able to find the data, render it, and you can clip the imagery. You can do some analysis using Google Engine as well.
Okay, I think I'll be done with this question. So, like, I guess so. If it's utilizing some sort of like foundational large language models, which ones are that are being used right now in those like?
Or you can use any. So you can use OpenAI, ChatGPT, or like Gemini.
And do you have a recommendation based on your experience? Which ones are like more powerful for geospatial?
They are pretty much so similar for large language model. This one is not really like into geospatial. Mostly just converting your natural language to some Python code that the program understands. So what I recommend is just OpenAI, the Codex model, because that one is $20. You can just monthly subscription. And you can also use your local model if you have GPU running locally. But I would recommend just this one, so that is you're not paying the API usage. Sometimes you might pay hundreds of bucks depending on how much you use. So for me, it's just $20. Then you just log in and then you can use for many tasks without having to worry about exceeding the spending.
And the last question I asked, what's your personal take on the evolution of like agentic AI in geospatial domain? What do you see or what do you expect in the coming few years, like how the geospatial work would evolve with AI? That's my last question. Thank you. Sorry, I asked it a lot.
It evolves just like the general AI like domain. It's to me, it's just we are not really create anything groundbreaking. I think we are basically adapt some of the latest model that you can do some transfer learning and then apply to geospatial. But the limitation is that all the large language models out there, most of them are not trained on geospatial data, so they don't really have a complex understanding of geospatial in those models. So you can do some text, you can do some reasoning, but if you're trying to like ask like some real for example, do some change detection and then just figure out how big is the area, it's going to struggle. They don't have those capability. Also, it needs a lot of GPU. But under the hood, I mean, right now most of the model basically just treat it as just a JPEG and PNG, and then just trying to do some compression. But they don't align to the other. They don't really have those things that running under the hood. It's just seeing that it's a vision, but they don't have spatial concepts. So it's still quite limited. I think we still has a long way to go to actually eventually. I mean, ideally, you want those large companies to train a lot of, or even just use the SETA embeddings in some of their models, training their models rather than just use JPEG and PNG without geospatial information. I don't know how the future is going to look like, but it's changing very fast. So some of the things that I present here today, it might be obsolete maybe in a year. Who knows? Because with all the natural language capabilities and also the computer vision, in the future, you don't need to write code anymore. You can maybe just ask like agent to write the code for you. Okay, I this image, I want to do the detection, just write the code. So the agent will write the code and then use your local environment to just do the execution. But I don't think those large like the company is going to provide like install those packages and then run those codes for you. It's just too expensive. But they can write the Python code and then you can take that and they can fine tune and then you can get the result using your own computing environment.
Great. Thank you, Sean.
All right. Thank you for these questions. We're going to wrap up right now. I'm sorry if we weren't able to get to all the questions. I know that Qiusheng has been very gracious at sharing his contact information, and I'm sure he wouldn't mind a separate email from someone asking a question later.
Mm.
Someone did ask about logging on to the platform. The platform, I-GUIDE uses CI logon to authenticate any of users. So if your university, I mean, as you know, it is possible to use OrcID or other ways to use CI logon. If you can't log on to the platform, make sure first you can go to cilogon.org and see what you need to do there. You can always reach out to I-GUIDE at the help email, which is part of our contacts too. So thanks again very much for sharing about this. Really appreciate the time that all of us were able to dedicate to learning about this. And stay tuned. I-GUIDE will have a next presentation a week from now from one of our other community champions. So thank you very much, everyone. The recording of this will be up in a little while up on the I-GUIDE VCO page. Take care, everyone. Bye-bye.
Thank you, everyone. Take care. Bye-bye.